Okay, so yeah, we talked about, okay. It's a control. Yeah, okay. So last class we spoke about how do we express various basic thermodynamic variables in terms of uh, in terms of energy components, and the most important one would be how uh, Gibbs energy with different conditions are related to is related to other uh, basic thermodynamic variables. Here we did a mistake last time. I have corrected that. So this one is fine. You know, del G by del P at constant temperature would be volume, but then the del G by del T at constant pressure would be negative of entropy, or entropy is negative of the del G by del T fraction, that's partial of G by T. Okay. Uh, so what does it mean physically? Because you know that volume and entropy are substances, or all of these things are things which you can measure very easily. Little difficult to measure is entropy, but you know that still can be done with the measurement of specific heat from different experiments. So S also is kind of easy to compute. But so that essentially gives you the idea of what's the Gibbs energy or Gibbs free energy of the system, and free energy of the system actually tells you whether the process or reaction would happen spontaneously or not. You know, this feasibility of the reaction, it's going to tell you. So if you look at so I've just you know taken these two things because these are very important. We are going to be using it more often while we continue our discussions towards phase stability and all. So simply, if you look at this mathematical form, it's what partial of G by P, okay, which is how the free energy changes with a change in pressure while you're not changing the temperature. So it's temperature being constant, how the partial of uh, Gibbs energy by pressure is changing. And if you want to put a plot, a physical representation of that, or in the thermodynamic coordinate space, you'd see somewhere like this. This is the variation of G over changing pressure and changing temperature, right? This is what it is. So this talks about the phase stability of the system or material system or whatever, a combination of materials. So in this, if you say that you've got to keep the temperature constant, that means if this is the temperature profile or the temperature axis, then one point of that would be constant temperature. And at that temperature, if you want to vary pressure, that's going to be the line here. That's a projection of the line here, right? That means corresponding to this line, the free energy change with at a constant temperature with varying pressure would be the curve like this. All right, would be the curve like this. So and in that curve, what does it mean? Del G by del P. The partial of G by P is nothing but the slope of it at every point that you want to say. You know, that's the slope of it. And then let's think about this. Del G by del P by T is V. V is what? V is the volume of material. Okay, when you normalize it, sort of molar volume of material. So can volume be negative? No, it's a finite volume. It's always positive. It's more than zero all the time because something is there. That means by virtue of this quantity, the slope would always be positive. All right. If the slope is always positive, that means it's going to be always on the rising kind of curve. And that's very important. That's the most important thing. All right. So you take a constant temperature. There's one point here, and then this is the constant temperature line and the variation in the pressure direction. And you want to plot the G in changing pressure situation, that's going to be the curve like this, and the slope of this is what is given here, is equal to V. All right. And much like the same way, if you look at the other one, is when you change, you keep pressure constant, and you'd like to see how the Gibbs energy changes with changing temperature. All right. That would mean this is the pressure axis, and then at one pressure means you pick this point. This is the pressure you want to see what's the change of Gibbs energy, and in that pressure, the changing temperature line would be this. Okay, and as this is a projection and you put it back onto the free energy space, that's what is about this line. So this is the edge of the whole curve, all right, which speaks about a constant pressure process. Okay, this is the whole surface, free energy surface. Okay, meaning it's a thermodynamic surface, a coordinate surface. Now it's a coordinate space where all thermodynamic parameters are represented. Okay, so this is the G curve or G surface, and in the G surface, the constant pressure, how the G changes with changing temperature is represented by this line. A projection of that onto the temperature pressure plane is going to be like this, where the pressure is remaining constant and the temperature is varying this way. Now in this, if you look at this, again you can talk about the slope. The partial of G by T is the slope, which is minus S. That we know from mathematics or thermodynamic mathematics. Now, like V, what about entropy? Entropy is always more than 1, isn't it? Entropy is always positive. On a changing reaction, that could be different, because you're talking about S1 to S2. This could be a negative thing or a positive thing, because that's we're talking about delta S. The change in entropy in a process can be positive or negative, although of course definitive boundaries are there. But when we talk about absolute entropy, that's always a positive quantity, isn't it? That means there's a little bit of disorder everywhere. It's only in the third law it speaks that at absolute zero temperature, that's where entropy could be zero, right? But anywhere else, since absolute zero is not attained as yet, and then all temperatures of practical considerations are much higher than absolute zero, so we don't have to be in that theoretical regime. Take it as a thumb rule that entropy is positive, entropy is significantly positive, talking about the temperatures that we operate as materials engineers. So when S is positive, this slope, a negative of S is a negative slope. So partial of G by T at a constant pressure has got to be a negative. Right? Slope is going to be negative. That means that's what is represented here. It's going to be going down all the time, right? So these are the knowledge that's going to be helping us, in constructing phase diagrams and stability diagrams for single or multi-phase materials. We will see that as we move on. So just to condense what we have spoken about, as S is always positive, greater than zero. G always decreases when the temperature is raised at constant pressure and composition, of course. When we are here not talking about addition of compositions and all that. The restrictions are that if for a changing temperature situation, we are not changing the pressure, we're keeping the pressure constant, and we're not allowing any other composition to come in, any other chemical species to participate in that reaction. And in this thing, you can always see that if S is increasing more, then what's happening? If the absolute entropy is higher for some reason, then the slope is more negative, because S is more positive. If S is more positive, then the slope is more negative. Okay, and in the changing curve, it will see that the G would change more rapidly. And here change meaning the temperature increases, G would decrease. That's going to happen more rapidly. Now, what would be the situation when we talk about the different phases of the same material? For example, let's talk about water. Okay, and water, its free energy or its Gibbs energy can change with temperature as well, as per this equation. Okay. Now, the free energy of water changes with temperature. The free energy of ice changes with temperature. And the free energy of steam also changes with temperature. All right. Now, in that situation, you know that the entropy of steam, it's much higher than that of the condensed phases. All right, be it ice or water. The entropy of 1 molar substance is much higher in steam than it is in either water or ice. That means the absolute entropy of steam is much larger. That means the change of free energy with temperature for steam is going to be much more steeper and steeper negative than it is for liquid or solid water. That's the point. So since the gaseous phase is more entropy, the fall of free energy, Gibbs energy, with temperature is going to be much more steeper, much more rapid. Okay, and that's the nature of the curve, which can give a clue that it's whether it's a solid phase, a condensed phase, or in a gaseous phase. So much like the same, I mean, you could see that here. We are talking about a Gibbs energy here. We are plotting, and then the Gibbs energy you're plotting here, and there's a temperature. it's a sort of a arbitrary line. It doesn't have to be scaled, but this is what represents the nature of the curve. Right? There's no numbers put into that. So if you look at it, the liquid and solid are kind of close by, right? And the change with the free energy and how does it change with temperatures is sort of given here. And you see that the curve of solid is kind of flattish, although towards a negative one. It's a negative slope is there. But then if you look at the extent of slope, if you look at the slope, it's less negative than liquid water. So liquid one, although crosses the solid at one point, and it has got significance in the sense that when it is going to be stable and when it's going to be not. Actually, if you look at it, this is going to be representing to 0 degrees Celsius. That's where the stability thing changes from solid to liquid. All right, but we'll talk about that at some other time. Here, if you look at it, the slope of liquid is slightly higher negative than that of solid. But if you compare the same thing with gas, it's a much more bigger slope, although it's going to be a negative slope. It's on this side, A positive slope would be pretty much like this. All right. So the gas slope is much more larger and more negative than either solid or liquid. And of course, true to our normal understanding of entropy, you'd see that the slope of solid is also lower than that of liquid. All right, the liquid is much more lower than that of the gases. The point is that, so since the slope is much more higher here, the extent of change over a unit temperature in the Gibbs free energy, the extent of change in Gibbs free energy over small variation in temperature is much more larger for the gaseous state than it is for the solid or liquid. All right. So here we are talking about 0 degrees Celsius, and here we are talking about 100 degrees Celsius. That's where the stability of at less than 0 degrees solid is stable, and from 0 degrees to 100 degrees liquid is stable, and more than 100 degrees gas is stable. And we see that the stability region is actually given by the Gibbs energy, and the Gibbs energy of solid is much lower than that of liquid or the gaseous Gibbs energy in the temperature region from less than 0 degrees Celsius. From 0 degrees Celsius to 100 degrees Celsius, the free energy of liquid water is lower than solid or gaseous. Yet again, the Gibbs energy of the gaseous state of water is lower in excess of temperatures of 100 degrees Celsius. That's what actually tells you at And all of these things we are talking about at 1 atmosphere pressure. Pressure is constant. Let's keep it at 1 atmosphere. So if we put 1 atmosphere to this, then this number becomes 0 degrees Celsius and this number becomes 100 degrees Celsius. And that's what tells you in which state H2O, what is going to be, whether it's going to be in solid state or liquid state or in gaseous state at different temperatures. Well, that's the indication of stability. And like that, if you, here it is again repeated, but then we can always go back this one and then talk about del G by del P at constant temperature, and you'll see that you get volume, and the description of that, we can see it here. You know, del G by del P at constant temperature. Let's talk about a constant temperature. We're not talk about 298 Kelvin or 25 degrees Celsius. We're not changing it, but we're trying to track what's the free energy and what changes when you keep changing the pressure. And you know that from that curve that del G by del T, del G by del P is volume, and you know that volume is a physical quantity, and then it occupies space, and it's a positive number. If it is positive number, then this slope is going to be positive. All right, and if you talk about the molar volume of gas and liquid and solid, you'd see that molar volume of gas is much larger than either liquid or solid, because these two are condensed phases. No, all right. So 18 grams of compared with 18 grams of ice or 18 grams of water vis-a-vis 18 grams of steam. You know, it's going to be much higher. So by virtue of the fact that it has got higher molar volume, the gaseous state, the slope is going to be much higher. Okay, in this is a positive slope, and it's going to be much higher. So, like we said in Gibbs energy for temperature relationships, if you look at the Gibbs energy change with a small or unit change in pressure, that's going to be much more significant in the gaseous state as it is in the liquid or the solid state, right? So that's what those are the indications that the free energy change gives us with regards to constant temperature and changing pressure, and with constant pressure and changing temperature, right? Okay. I had left that in the last time to discuss about that, so I thought we should complete our discussions on that. Okay, now we talked about exact differentials, and then we talked about Maxwell relationships, right? And I think you'll be able to calculate those relationships, and then prove some thermodynamic identities that we'll give in the later stage. And we also talked about Gibbs-Helmholtz equation, which that's where we had stopped our discussion last time, and we will see its implications in subsequent times. But let me before that complete some other aspects before closing. So we talked about up till now we've been talking about closed systems where there is a material system of combination of gases or solids and gases, and liquids and solids and gases, or any combination of that, where it's closed and nothing sort of goes in and nothing goes out. Now, if we keep the system open, in the sense that we can keep the system amenable to change in composition. For example, if we've had a system of ice and water, and I should be able to add more water to it, take out ice, or put in more ice, or put some steam, depending on how you can sort of change it. And if you are able to do that, again we talk about stability, right? How the system is going to attain the lowest free energy. That's our objective. And with the changing of this composition, how things will change, that is defined in a slightly differently in an open system, where you have a number of species and you want to track the changes in free energy with the introduction of one species while the others kept constant, which is what is written here. The DGs, the overall change, overall small change can be tracked with the combination of small changes that happens over different places, right? That you can write it, since G is a function of, this is the temperature and pressure, those are the independent variables, and then it's also a function of compositions. Now, because we made the system an open system, and that you're allowing things to come in and things to go out. Okay, and you like to see the changes these things bring in G. Okay, so we want to track the overall change in composition dG. That will be partial of G by T dt, while others are kept constant, P and all other compositions, plus partial of G by P, while temperature is kept constant, while all the other compositions are kept constant. So these two numbers are pretty much similar to a closed system. Then we are not talking about the incoming or outgoing of any other chemical species. But then you'll have to add other things where this part comes about the open system. All right. You see the change in the free energy with the change in the introduction of a component Ni. Ni is, let's say, is one kind of component. When you add on the little bit onto it a little bit, what's the change in del G? What's change in G, which is del G? Okay. So partial of G by Ni dNi plus partial of G by Nj dNj, while T and P and Ni and other components kept constant, but you still keep varying Nj. Likewise, so you have 5 components, you add 5 individual changes in those compositions where each composition changes and other 4 remain constant, and all of these things you put together along with the changes in independent variables. All of these things put together give you the small change, the overall small change in the free energy system. All right. And if you simplify it, if you sort of talk about a closed system, then all of these terms become 0, and it takes the form of dg is vdp minus s dt, which is the one of the most profound equations in thermodynamics. All right. So let's okay. Now, okay. So to sort of give a clearer idea of what this thing is all about, let me talk about a very small or very simple example. I don't know how appropriate it is. If you have a pen and paper, you can perhaps take note of it and then see how if you can participate in the discussion. Let's say I have a fruit basket. All right, I have a fruit basket where I have 5 apples, okay, of 10 rupees each. Let's say and 10 oranges of 5 rupees each. And let's say 10 guava of 3 rupees each. And let's say 10 lemons of 2 rupees each. These are random numbers and you can calculate, right? So how many? You have 3 different 10s and then 5. So you have 35 fruits, 35 numbers of fruits. And if you look at it, the whole price or value of the basket, you will see that is 550 and 10 into 550, 100, how much it is? And 3 into 10, 30 plus 10, it's 140 rupees. All right. So you have 140 rupees of the value of the basket with 35 fruits. All right. Now, can you calculate? Think about it. If you add one more apple to the basket, all right, how's the total value changing? The total value of the basket becomes 150 rupees. All right, but the number of fruits become 36. Because you already have 35 fruits, and then you're putting one apple, they becomes 36. And then you can calculate what's the average price of a fruit. From the 150 35 system, now 140 35 system, now it becomes 150 36 system. You'd see that the price, overall price, a price per fruit is slightly increasing. Because what was the average price in the 140 35 system? You're putting an apple which is 10 rupees each. When you're putting into the system, you're actually raising the average price. On the contrary, in the 140 35 system, or 140 rupees, right? Yeah. 140 35 system, if you're putting a lemon to it, which is 2 rupees value. All right. Even then, you are having 36 fruits, and then but the overall price becomes 142. So if you look at what is the change in the price of average price, the average price is actually coming down. So that's a very bad example of how free energy of a material system would change, right? If you talk about the unit prices are to be the molar free energies of the each individual things, okay, and then the value of the basket is this G, okay, that's the overall value, okay, and then when you talk about the average price of the basket, average price of a fruit in the basket, that would become G by the number of moles that is present here. That's a molar energy, molar free energy. Right. So how do you see that the total, what's the overall change if one fruit is added to the system? Is, that's overall change would be that when you add a single type of fruit in the system. Right. Now, if you just talk about the change in the price of the system with the introduction of one type of fruit, okay, which is equivalent to this one, that's del G by del Ni, while others are kept constant, right? So this quantity is called the partial molar free energy. Okay, it's a molar free energy, but then you are considering this molar free energy with only the change with the introduction or uh, deduction of one particular type of component, while others are kept constant. In that sense, it's called partial molar free energy. And a generic term that we use for this is called chemical potential. And this chemical potential is kind of the driving force. It's a driving force of the individual components, right? So if we and if we talk about the change in free energy with change in Ni, that's mu I, and we talk about the change in free energy change in Nj, that will be called mu J, and so on. And therefore, the open system and its overall free energy change is actually a combination of VdP minus SdT. These are from the independent variables, plus the overall changes of the components of each components in the form of mu I dni. That means mu1 dn1 plus mu2 dn2 plus mu3 dn3 and so on and so forth. And this dn is the change in the number of moles, and I is the type of material that you're changing. It's component 1 or component 2 or component 3 and things like that. So this eventually gives you the total change in free energy of the whole system, while considering all the sort of available components in the system. All right, and accordingly you can here we talked about dg, we talked about the change in free energy and how this chemical potential is affecting that. And what we did is we simply modified this thermodynamic equation with the addition of mu I dni taken over from species I to n. N can be anything. N can be number 5 or 6 or 20 or anything. That's all. So likewise, all other thermodynamic energy functions can be also changed to incorporate these two these component, making from a closed system to an open system. That's what is written here. You have du is TdS minus PdV. This is what we already know, and here you add this one. Okay, and all of this over changing number of components, and that brings down to du is TdS minus PdV plus the chemical potential term summed up over all species, all available species. Likewise, dA can be written like this. This is what we know already, and you add the chemical potential term. Likewise, in dH form, you also add the chemical potential term. So you'd see that there's a sort of a relationship here. You'd see that if you talk about the characteristic function as U, then the independent variables become S and V and the composition N. And this is for an open system. We talked about Q and SV, that's for a closed system. Now, since you're making the system open, now you're allowing materials to go in and go out, then the same characteristic function, energy function, is now is influenced by this independent variables S and V and N. And for enthalpy, this S and P. And for Helmholtz energy, it is T and V. And for Gibbs energy, it is T and P. You see that there's a commonality. If you're talking about the free energies, okay, these are the two free energies, right? And these are the two energies. These are the energies and these are the free energies. And what are the free energy? The free energy is in combination with the entropy part, in combination with the entropy part. Whereas the energies, other energies, which is the internal energy and enthalpy, these are not in combination with the temperature part. And the difference between these two is that this is all work, and this involves all kind of work, including the pressure volume work. This one doesn't include the pressure volume work. All right. So here, since it includes the pressure volume work and it's an energy function, you can see that the variables, independent variables, are entropy and pressure. All right. But in internal energy, it's all about entropy and volume. U is connected to CV, H is connected to CP. That is P and V, these two systems. We talk about the free energies. Here, temperature is going to be an independent variable all the time. All right, we're talking about, entropy has to come in here, and the entropy can come with connection with temperature. All right. And as you know that free energy, Helmholtz energy is connected to internal energy here. And that's a constant volume process. All right. And Gibbs energy is connected to enthalpy, and that's for constant pressure processes. All right. So these are the characteristic functions, and these are the independent variables, and that's it. So we'll stop it for today and then see how we can take this discussions forward, understanding a phase, one single component phase system to begin with, and then gradually will evolve into multi-component systems. All right. So I'm stopping the recording. If there are questions, we shall take some questions. Yes.